Hi everyone, and welcome to another video in my Operating Systems Concepts video series. In this video I want to talk about memory layout, that is, how C programs manage their memory and what it means for you as a programmer. Some disclaimers are that I'll be using C as usual, I'm running on Mac OS, and I'll be using 32-bit x86 in a few places. Alright, now let's get started. Most people have probably heard the term memory in terms of computers before. Memory is just a physical chip in your computer that stores data for your programs. Memory is often called volatile because it requires power to maintain the memory. If your computer shuts off, for example, you lose everything in memory. That's why your computer usually has a disk, a hard drive, or a solid-state drive that is persistent or non-volatile. Even if your computer shuts down, everything on disk is left intact. But in this video, we'll focus on memory. Now, to a program, memory looks like a giant array. Now, how do people interact with memory? Here's a small analogy. Just like houses on a street have addresses, each piece of data in memory is also given an address. Memory is usually byte addressed. That is, each byte, or group of 8 bits, is given an address in memory. Just like in the houses example, each house on a street has an address, but people within the same house don't have separate addresses. So whenever you want to access memory, the absolute smallest unit you can deal with is a byte, or 8 bits. And oftentimes, it's better if you access memory in words, which are usually 4 bytes if you're on a 32-bit system, or 8 bytes if you're on a 64-bit system. The 32-bit or 64-bit is just an indication of the word size. 32 bits is 4 bytes because each byte is 8 bits. And likewise, 64 bits, if you divide by 8, that's 8 bytes. Now let's do some quick math here. If you're on a 32-bit system, that means the word size is 32 bits. Or in other words, every address is 32 bits long. Now with a 32-bit address, you can address up to 2 to the 32 things. And since each thing we address is a byte, your memory can have up to 2 to the 32 bytes. If you do the math, 2 to the 32 bytes is approximately 4 gigabytes. So this is usually kind of at the upper limit of what most computers have today. That's why oftentimes your computers are actually 64 bits, which means they can address up to 2 to the 64 bytes in memory, which is really quite massive. Oftentimes your computer doesn't even use the full 64 bits of address space because that's just far more memory than the computer actually has. Alright, now that we've talked about what's in memory, the next question is, what can you do with things once they're in memory? There are two operations that are pretty common sense, that is read and write. There's also something else you can do with memory, and that is execute it. Essentially what happens is that the instructions of your program are loaded into memory, just like any other data. That is, your operating system reads data from your hard drive and writes those bytes into memory. And then when you run the program, your operating system actually executes instructions from the address at which you loaded your program. So your computer can also execute data in memory. You have to be a bit careful with what you execute because you don't want someone to, for example, supply data to your program that your program then runs, and then your program could be completely compromised, right? Because someone could tell your program to run whatever they wanted. So oftentimes your operating system has protections, like this area of memory is executable but not readable or writable, or this area of memory is readable and writable but not executable. Things like that, to make sure that you don't execute the wrong instruction. Most of the time though, the distinction between what you intend to read and write will be clear compared to what you want to execute, which is just your source code. Alright, now let's jump into some actual code. Here I have a few programs written in C, memory and bad. Let's look at memory first, so let me open that up. Alright, this basically has a few functions that explain how the C memory layout works. Let me first talk about what this program does, and then I'll talk about what it's intended to showcase. So I have this function called stack, and basically what it does is it calls itself recursively in a loop, so it'll run up to 5 times in this case, and each time it creates this temporary variable called temp and sets it equal to 1, and at each iteration it prints out the address of that temporary variable. Once the program's done that, it calls this heap function. The heap function just allocates a buffer of 128 bytes and prints out the address of that buffer. And finally, the global function sets this global variable y equal to 200, and it also prints out the address of string, which is defined up here. It prints out the address of x and the address of y. Now let me give a little bit of background about what this program is intended to show you. The main idea is that C splits its memory use into 4 main regions. At a high level though, the 4 sections are text, data, the heap, and the stack. Let's go over them one by one. The text section of memory stores the text of your program, that is, the code that your computer should execute. Of course, this is not exactly the source code, because your compiler will compile down the source code into assembly and machine code. Nonetheless, the text section is where all your program instructions go. The next section is data. Data contains any global variables you declare. Some people make the distinction between the uninitialized data section and the initialized data section. So sometimes if you have uninitialized variables, they will be stored in a different section of memory. But either way, it's still within the umbrella of the data section. Alright, the next two regions are the heap and the stack. This is where programs get interesting, because the text and data segments of your program are determined at compile time. That is, when you compile your program, the compiler knows all the global variables that your program contains, and so it can allocate a fixed-sized global data section. The stack and the heap, however, change their size during your program's execution. The stack is usually at high addresses and goes downwards, whereas the heap is at lower addresses and goes upwards. The stack section is where all local variables are stored. For example, the temp variable here is allocated within the scope of the stack function, so it's a local variable, as opposed to a global variable like stir x or y. So the temp variable will be allocated on the stack. The stack section of memory, unsurprisingly, works as a stack. When you're in the main function and you call the stack function, the computer pushes a stack frame onto the stack. Remember that the stack region of memory starts at high addresses and goes downward. So if the end of main's stack variables is over here, when main calls the stack function, it allocates new space on the stack and pushes the arguments to stack onto the stack. Now when the stack function begins executing, it allocates more space for its local variables, growing the stack a little bit more. Now when stack itself calls other functions, in this case stack calls itself recursively, it allocates even more space for the local variables of those other functions. Now when a function returns, it pops its stack frame, that is, it decreases the size of the stack. When all functions have returned, and main takes control again, the stack should be the same size as it was before main started calling any functions. Alright, the last section of memory is called the heap. The heap is another dynamic section of memory, that is, it grows and shrinks as your program executes, but it's not exactly tied to function scopes. So in this case, when I allocate buffer here using malloc, which allocates data on the heap, the data pointed to by buffer is still valid even after I exit from the heap function. So the data pointed to by buffer is not tied to any one function frame. Alright, let's run this program. Also note that each time you run the program, the addresses might change a little bit, and if you run it on your own computer, you might get different addresses. This is because your operating system usually randomizes the places where it puts the stack and heap in memory for security reasons, and so don't worry if your addresses are inconsistent. Here we're only interested in the relative patterns, so where these addresses are relative to each other. So remember that temp was on the stack, and at iteration 1, so this is the first call to stack, the address of the temp variable was over here, at something ending in 778. Now, at iteration 2, the address of the temp variable was over here. Note that it decreased by 20 in hex. Also note that these are talking about different temp variables, right? So this is the temp variable corresponding to the first iteration. This is a new variable that was allocated in the second recursive call to stack. This is the temp variable in the third recursive call to stack, and so on. So these aren't all the same variables. It's not like the variable is changing places in memory. It's just that we're referring to a different variable each time. And so you'll notice that each time the address is going down by 20 in hex, which is 32 in decimal. So what this is saying is that the difference between the first temp at the first iteration and the location of the temp variable allocated by the second iteration is separated by 32 bytes. So this is consistent. This should make sense because remember that the stack goes downward. So if the local variables of the first stack function call is here, then when stack calls itself recursively, the local variables for the second recursive call will be below it, and so on. For the third recursive call, that should be below the second recursive call, and so on. Alright, now you'll also see that the address of buff is 7ff2 something, whereas the address of the temporary variables on the stack was 7ffe. So these are separated by quite a large space, 7ffe versus 7ff2. This is because buff is on the heap, so buff is not really tied to these stack frames. Next, you'll see that the string x and y, these are our global variables, are even farther away. They're at hex 10d something something something. So these global variables are allocated in a much lower memory address. Again, this should be consistent with what we expect, because the stack starts at high addresses and goes downward, which is what was happening with our temp variables. The heap starts at lower addresses, which makes sense because buff was at 7ff2b something, whereas the stack is up here at e something. And then the global variables are even lower. They're at hex 10d something, right? So we have the stack on top, the heap below that, and then far below that is the global variable section. Now there's one section that we missed, which is the code section. That's not shown here, but the way I can see that is by using objdump. So let me just objdump -d memory, and you'll see that there's a bunch of data, and these instructions are stored at hex 1000 something. So they're below the global data section of memory. So again, that should make sense. We have data on the bottom, then the global section, then the heap, and then the stack. Now you might be wondering, why do I care about this? And let me show you one quick reason why. So I have this program called bad.c. Warning, this is bad code. You should not do this in real life. But it's just an example of what you can do if you don't think about where your data is being stored. So I have this function called badGetString. Again, this is bad code. You should not write this. But essentially what it does is it creates a variable called string and sets it equal to hello. And remember that we're not malloking data here, so this string will be stored on the stack. And then I'm printing it out and returning the string. And in main, what I'm going to do is I call badGetString to get the string, and then I run this recursion function that just does some recursion, doesn't do anything interesting. And then I print out string, right? So what do you expect to happen? Well, over here at this printf, we should get hello, right? That would make sense. Then when we return the string to main, string will be set to that pointer. Then we'll do some recursion, and then we'll print out the string again. So you might expect that we'll get hello twice. But let's see what happens when I run this. So I'll do /bad, and we get hello once and nothing the second time. So you might be wondering why this is. So let me open up the code again. So when we called badGetString, hello was stored in the stack frame of badGetString. Now when badGetString returned back to main, this is now below the end of the stack. Then the recursion function is called, and it allocates new stack frames for calling itself, and it recurses 100 times. So the data in the string gets completely overwritten. So when I printf the string the second time, it's pointing to bad data, and so we don't really get anything useful. I'm not even sure what's at that memory address anymore. So you definitely shouldn't be doing this. So there are two ways that you might want to fix this program. One is by using a static string. So if I change this to be char star string equal to hello, this no longer points to data on the stack. So your compiler will actually put this hello string literal in the data section of memory, and then just create a local pointer to the hello address. Then you're returning the address, which is completely fine. C copies addresses when it returns anyways. And so this should work. So let me run this. Let's do make bad. And then if I run bad, you'll see we get hello twice. The other solution you could use is to malloc the string. So you can malloc, let's say 10 times size of char. So this is allocating 10 bytes since each character is 1 byte. And then we can do sprintf, string, and hello. So this would basically copy the string hello into the string array. Now, technically we should also free the string. We don't want memory leaks, but I'm going to ignore this for now. Also note that this solution is not any more efficient than the previous solution because we still have to store this hello string in the global section of memory. So this is not more efficient at all. In fact, it's probably less efficient because we have to do this extra sprintf. But anyways, let me save and quit. Let's make bad. And if I run bad now, you'll see we get hello twice. Alright, great. So that wraps it up for this video. So you've hopefully gotten a taste of how C manages its memory. And you've also seen what happens if you aren't careful about how you manage your memory in C. Of course, there's a lot more depth into how we could go into about how virtual memory works, and that's an interesting topic that I'll cover in a future video. Hopefully this video was interesting, and I'll see you next time. Thanks.